Welcome to While We Were Distracted, the podcast where we explore topics that often get overshadowed in the rush of daily life.
Imagine for a second that you're stepping inside this newly constructed state-of-the-art server farm. But instead of a technician, like walking down a freezing aisle to swap out a malfunctioning hard drive, you watch them carefully measure out this dense biological sludge.
Yeah, actual sludge.
Right. It's this nutrient-rich fluid formulated to mimic human cerebrospinal fluid. And they're preparing it because the processing units in this facility are constantly depleting their nutrients. So to you, our resident learner listening in today, welcome to our deep dive. We are looking at two really fascinating pieces of reporting from Futurism and Live Science that detail the arrival of biological data centers.
It sounds totally made up.
I know, it sounds crazy.
Yeah.
We're talking about machines powered by actual living human brain cells.
Yeah, the imagery of technicians just feeding literal sludge to a server rack is, it's jarring. I mean, it feels straight out of a science fiction horror movie.
Absolutely.
But this is actually a very serious, highly funded engineering effort, and it's aimed directly at, one of the tech industry's most immediate threats.
Yeah. Energy crisis.
Exactly. The current trajectory of artificial intelligence and hyperscale computing is just slamming into this insurmountable wall when it comes to energy consumption and thermal output. Like, silicon chips are maxing out our power grids right now. So biological computing is being positioned as this desperate but wildly efficient alternative.
I mean, I understand the desperation for efficiency, sure, but jumping straight to human brain cells feels like a massive leap. When the sources say human neurons, my mind immediately goes to some, dystopian organ harvesting scenario. Like, where are they actually getting the biological material to build these processors?
Right. No, it's not like that at all. They are entirely lab-grown.
Okay.
Yeah. The company pioneering this is an Australian biotech startup named Cortical Labs. Basically, they use stem cells and they coax them into becoming neurons.
Okay.
And then they deploy these cells into a proprietary system they call the CL1. So at the heart of every single CL1 unit is this culture of roughly 200,000 living neurons.
But wait. 200,000 neurons just floating in a jar. Like, that can't run a software program. If it's just this wet biological mess, how do you even get a digital signal in and out of that?
Well, so they don't just float. The neurons are actually cultivated directly onto a silicon microelectrode array.
Okay, what does that look like?
Picture thousands of microscopic metallic needles. The cells naturally grow over, around, and physically connect to this grid.
That is wild.
Yeah, and that silicon array acts as the translator. It allows an external software program to stimulate the living cells with targeted electrical voltage, and then it records the resulting electrical ripples that the neurons, fire back in real time.
Okay, let's unpack this, because the physical maintenance required to keep this hybrid system alive is where the reality of the technology becomes almost absurd to me.
Oh, it's incredibly demanding.
Right. According to Cortical Labs CEO Hong-Wing Chong, those 200,000 neurons are just relentless. Like, they are constantly consuming the oxygen and glucose suspended in their fluid. It's not something you just plug into the wall and forget about. No, not at all. Every 24 hours, facility staff have to physically intervene. They drain the depleted fluid and pump in fresh biological sludge just to prevent the computer from starving to death.
And the fluid is really only a fraction of the necessary life support.
Yeah.
The entire atmospheric environment around the processor has to be, obsessively controlled.
Yeah. The reporting from Futurism highlights that the operational floor feels more like a highly regulated greenhouse than a tech facility.
Exactly.
Technicians have to shroud the computer in a specific blend of nitrogen and carbon dioxide to maintain exactly a 5% oxygen level. Earth's natural atmosphere is, about 21% oxygen?
Yeah, around there.
Which would completely fry these cells. I mean, in the human body, neurons are protected inside the skull. Out in a Petri dish, exposing them to standard room air causes oxidative stress and literally kills them. They require a completely alien atmosphere just to function. It's basically a highly advanced biological Tamagotchi.
A Tamagotchi is actually a great way to put it. You are looking at a processor that requires climate control, specific barometric pressure, constant nutritional replacement, and, active biological monitoring. The hardware is fragile, living tissue.
Which raises an incredibly obvious question. If maintaining the hardware requires a literal intensive care unit, why go through the nightmare of using it?
Right.
A silicon chip just sits there and works. If they are going to deal with this much biological overhead, this CL1 system has to be capable of something profound.
Yeah, and proving that capability is the fundamental challenge here. I mean, how do you objectively prove that a cluster of cells isn't just twitching randomly in a dish, but is actually, processing information?
How do you measure that?
Well, Cortical Labs decided to map the microelectrode array to classic video games. A few years ago, they made headlines for teaching these cells to play Pong.
Pong is impressive as a proof of concept. Sure, you track a ball, you move a paddle. But their recent benchmark with the CL1 system is just magnitudes more complex.
Oh, absolutely.
They mapped the array to the classic 1993 first-person shooter, Doom. Like the biological computer is navigating a 3D environment. It is controlling multiple complex game mechanics and actually dealing with enemies.
Yeah, the sheer complexity of Doom is really what makes this a watershed moment. But to understand the significance, we need to look at the mechanism of how the cells actually learn to play it.
Right.
Because it fundamentally differs from how you program a silicon chip. The process relies on a closed feedback loop that's driven by a biological imperative called homeostasis.
Homeostasis, okay.
Yeah. Basically, living cells desperately want a stable, predictable environment.
They want a calm rhythm.
They crave it. So when the neurons are playing Doom, and they perform an action that is beneficial to the game state, like, say, moving away from an enemy, the software sends a smooth, predictable electrical rhythm back into the cells through that silicon array.
Okay, so a reward.
Sort of, yeah. But when they perform poorly or fail, the software blasts the array with chaotic, unpredictable electrical noise.
Oh, wow. It's like sitting in a small room where the microphone is generating that terrible high-pitched acoustic screech.
Exactly.
Like, if that happens, the people in the room aren't going to just sit there. They're going to scramble, cover their ears, unplug cables, maybe physically move the speakers until the noise stops. They completely reorganize their environment to escape the chaos.
That is a perfect physical comparison for what is happening at a cellular level here. The neurons experience that chaotic electrical static as a highly aversive state.
They hate it.
Yeah, they hate it. To escape it, they physically reorganize their synaptic connections. They continually shift their internal pathways until they stumble upon a configuration that results in that smooth, predictable electrical rhythm returning.
Wow.
So over thousands of iterations, simply by trying to avoid electrical chaos, the physical architecture of the cells settles into a pattern that corresponds to successfully playing Doom.
I mean, I am amazed by the biological adaptability. That's incredible. But I have to push back a little on the utility here. Teaching cells to escape electrical static so they can navigate a 90s video game is an incredible lab stunt. But how does that translate to actual computing? Like, dodging a pixelated demon in Doom is not calculating a spreadsheet or generating an algorithm.
What's fascinating here is, to understand this, we have to completely dismantle our standard definition of computation.
Okay.
The Live Science article introduces the core mechanism at play here, which is called reservoir computing.
Reservoir computing.
Right. In traditional computing, you are dealing with rigid, deterministic instructions. A silicon processor relies on Boolean logic gates. You program a strict set of rules, and the processor executes those mathematical steps perfectly.
Right. It's just highly advanced math operating at light speed.
Correct. But reservoir computing abandons that strict programming completely. Instead, it utilizes a highly complex dynamic system, which is the reservoir. Imagine dropping a pebble into a pond. A traditional computer would try to mathematically calculate the exact physics of every single resulting water ripple based on the weight of the pebble, the density of the water, wind speed, all of that.
It does the math.
Right. A reservoir computer simply drops the pebble into an actual physical pond, lets the water ripple naturally, and then measures the waves at the edge.
Oh, wow. So the biological neurons are the pond.
They are the pond. The software isn't telling the cells how to play Doom. The software feeds the game state into the network as an electrical signal, lets that signal reverberate through the massive complexity of those 200,000 synapses, and then uses a simple readout layer to interpret the resulting pattern.
That is mind-blowing.
The cells possess this incredibly rich internal physical dynamic. You aren't forcing them to do math, you are harnessing their natural ability to transform inputs into complex patterns.
So we aren't building a faster calculator. We are building a system that naturally adapts to its environment.
Exactly. And realizing that biological systems process data completely differently than silicon is exactly why the tech industry is suddenly willing to tolerate all this messy biological upkeep.
Because we are hitting the limits of conventional chip design.
Yes, exactly.
Let's examine those limits, because we all know AI is demanding more power. But the underlying physical constraints are rarely discussed. The modern hyperscale data center the ones run by Google, Amazon, Microsoft. It's essentially a massive thermal management problem.
Oh, entirely.
We've spent decades shrinking transistors down to the atomic level, right?
Yeah.
Just trying to pack more of them onto a piece of silicon. But we are hitting the wall of physics. When you pack billions of transistors that tightly and run them at high speeds, they generate an astronomical amount of heat.
Yeah, it creates a massive thermal bottleneck. You need huge cooling infrastructure just to prevent the silicon from literally melting itself.
Right.
And we also suffer from what's called the von Neumann bottleneck. Traditional computers separate the memory from the processor. So moving data back and forth between where it is stored and where it is actually calculated requires a tremendous amount of time and just brute force electricity.
And compare that massive brute force approach to the ultimate biological processor. I mean, the human brain performs incredibly complex pattern recognition, it parses language, it learns continuously, and it does all of this while operating on roughly 20 watts of power.
It's incredible.
A standard household light bulb uses more energy than the human brain.
Yeah, and the architecture of the brain solves that von Neumann bottleneck naturally. A synapse serves as both the memory storage and the processing unit simultaneously.
So there's no moving data around.
Right. There is no massive data transfer wasting energy. The biological efficiency is so far beyond our best silicon that Cortical Labs is explicitly targeting it. CEO Hongwing Chong actually told Bloomberg that a single CL1 unit requires less power to operate than a handheld digital calculator.
Less power than a calculator. I mean, when you're comparing that to traditional servers that require megawatts of power and millions of gallons of cooling water, the appeal of a biological alternative becomes undeniable.
Yeah. Chong even predicts that these biological networks will eventually surpass traditional computers in processing speed. But, raw speed in mathematics isn't really the primary advantage here. The true value is adaptability in the face of uncertainty.
I think the clearest way to visualize the divide between these two technologies is to look at a modern silicon processor as a high-speed bullet train.
Okay, I like that.
Right. The train is breathtakingly fast and incredibly precise, but its performance is entirely dependent on perfectly laid, rigid tracks. That represents the deterministic math.
Right.
If you place an unexpected obstacle on the tracks or a rail breaks, the system crashes. It cannot adapt its route.
It just fails completely when the parameters change.
Exactly. But the biological computer, the neural network, it functions like a rugged off-road vehicle. If you place that vehicle on a perfectly paved straight track, the bullet train will beat it every single time. Silicon dominates clean mathematics.
Yeah.
But if you need to navigate a dense, unmapped forest with no roads, the bullet train is totally useless. The off-road vehicle can dynamically adjust to the mud, it can climb over fallen trees, and find a path through the chaos. In computing terms, that unmapped forest is noisy data. It is sensory processing, voice recognition, and dealing with real-time uncertainty.
And that unpredictable terrain is exactly what modern artificial intelligence is struggling to navigate right now. AI models are trying to parse the nuance of human sarcasm, or identify a specific face in a blurry crowd, or safely guide a vehicle through a sudden snowstorm.
Yeah, those are not clean mathematical equations.
Not at all. They are messy, sparse data environments. And biological systems evolved over millions of years specifically to organize that kind of chaotic sensory input into actionable decisions.
So if living tissue is this uniquely qualified to handle the exact problems AI is facing, and doing it at a fraction of the energy cost, the natural question is, why aren't we there yet? Like, why are tech giants still pouring billions into building larger silicon factories? Why isn't the entire industry migrating to biological data centers today?
Well, because the engineering bottlenecks of working with living tissue are just monumental.
They're huge.
Yeah. Scaling this up from a lab experiment to reliable enterprise infrastructure introduces variables that computer scientists have never really had to deal with before.
Yeah, the sources outline a brutally slow setup process. Preparing a single machine takes Cortical Labs roughly a week of custom hands-on configuration based on the specific needs of the customer.
Right, because you cannot simply stamp out biological processors on an assembly line. When you manufacture 1 million silicon chips, you know with absolute certainty that every single chip will behave identically.
Perfect reproducibility.
Exactly, but biology has inherent variance. If you grow 2 separate cultures of 200,000 neurons under the exact same conditions, their synaptic pathways will develop differently. They will adapt to stimuli at different rates. So guaranteeing standardized, predictable performance across thousands of biological units is an entirely unsolved engineering challenge.
Not to mention the degradation. Silicon chips don't age the way cells do. These neural cultures have finite lifespans. They eventually die, meaning your hardware literally expires.
Right. And beyond the hardware limitations, we are facing a massive gap in basic scientific understanding here. The Live Science article features a really striking observation from Steve Ferber. He's a prominent computer scientist and mathematician.
What did he say?
He points out that despite a huge amount of progress in neuroscience over the decades, the fundamental principles of how the brain actually processes and stores information remain a mystery.
So we don't even fully know how the brain works yet.
No.
We are trying to engineer a machine out of components that we don't possess the instruction manual for. I mean, we can see the neurons reorganizing to play Doom, but we don't fully understand the underlying mechanics of how a complex thought or a memory is actually encoded in that tissue. Trying to optimize a general-purpose processor when you are basically stumbling in the dark regarding its core function is incredibly difficult.
It is. And as we stumble forward, attempting to connect larger and larger arrays of human brain cells to increase processing power, we are running headfirst into a profound ethical threshold.
The moral elephant in the room, the question of consciousness.
Exactly.
Because we are using human neurons. Now, the sources make it clear that the 200,000 cells currently sitting in a dish playing a video game possess nothing resembling human awareness.
No, of course not.
They're simply reacting to localized electrical stimuli.
Right. Current iterations are essentially biological reflex engines, but the explicit goal of the industry is rapid scaling. So what happens when we transition from 200,000 cells to 2 billion or 20 billion? At what level of complex integrated adaptation does a reservoir stop being a simple input-output mechanism and actually cross the line into experiencing its environment?
And how would we even measure suffering in a system that has no sensory organs or voice? If they find chaotic electrical noise, highly aversive, which they do, and we subject them to it continuously to force them to learn at a massive scale, does that constitute distress?
It's a huge issue. Researchers are actively demanding that the scientific community establish clear ethical guidelines right now. They recognize that the technological capability to build massive neural arrays is totally outpacing the philosophical framework required to manage them responsibly.
Yep.
Determining the threshold of consciousness in synthetic biological networks is a debate we have to settle before the technology matures, not after.
It is a staggering reality to process. We're dealing with extreme hardware fragility, unpredictable biological variants, a lack of fundamental scientific understanding, and a looming ethical crisis regarding consciousness. Yet, despite all of those massive hurdles, this tech is not staying in the lab. It is actively being commercialized right now.
Yeah, the speed of commercialization is perhaps the most indicating factor of how seriously the tech sector takes this potential. They aren't waiting for perfection.
No, they're not. Cortical Labs has already launched a biological cloud computing service.
It's crazy.
Right now, a software developer can literally pay for API access to execute code on a stack of 120 CL1 units. Think about the mechanics of that. A programmer writes code on their laptop, sends it to the cloud, and that code is translated into voltage spikes that zap living human tissue resting in biological sludge in Melbourne.
Sounds like magic.
It really does. The tissue reverberates, the output is translated back into digital data, and the result is sent back to the developer's screen.
And they are currently operating those 120 units at a bench scale level. But their physical expansion plans are very aggressive. They are actively building a new data center facility in Singapore, designed to house up to 1,000 CL1 units.
1,000?
Yeah, they are betting millions of dollars on their ability to stabilize and scale this infrastructure.
We are moving from small lab tests to commercial data centers housing thousands of living processors. And to you, our learner, absorbing all of this. Consider the unique vantage point you have right now. Over the coming years, you are going to be inundated with headlines about artificial intelligence draining local power grids, halting construction projects, and demanding just unsustainable amounts of water. You will hear endless debates about the energy crisis.
Definitely.
But you now possess the inside track on the wildest, most unorthodox solution being built to fix it. You understand the bizarre biological alternative quietly expanding in Singapore.
It really represents a radical humility in the face of nature. I mean, after decades of relying entirely on our ability to engineer better silicon, we are finally looking at the biological world and admitting that evolution has already engineered a vastly superior processor.
Yeah.
The challenge now isn't inventing a better computer. It is learning how to harness the one nature already perfected.
Our journey through these sources today has been a profound shift in perspective. We began with the unsettling reality of technicians managing atmospheres of 5% oxygen and swapping out cerebrospinal fluid just to keep a motherboard alive. We unpacked the acoustic feedback-like mechanism that drives living neurons to seek stability by mastering a classic 90s video game. And we explored how the dynamic ripples of reservoir computing might be the only way to break through the thermal walls holding back the future of artificial intelligence.
This raises an important question, though, and it forces a philosophical shift that we will all inevitably have to navigate. It alters our basic vocabulary regarding infrastructure.
I can only imagine, what does IT support even look like in a biological data center?
Well, consider the reality of a massive data center running entirely on living neural tissue. When a server goes offline or begins to falter, the language of the facility changes entirely. Will the technicians be deployed to repair hardware, or will they be responding to heal tissue?
Oh, wow. That completely changes the dynamic.
Exactly. How humanity's relationship with technology will evolve when our computers are no longer disposable inorganic objects, but living patients that require careful feeding, medical intervention, and precise life support. That is a question that will redefine the next era of computing.
If nothing else, it ensures you can never look at a server rack the same way again. Just remember to maintain the climate control on your biological processors, or they might refuse to run your code. It is an incredibly surreal technological frontier, but it is arriving much faster than anyone anticipated. Thank you for diving into the depths of this paradigm shift with us today. Keep seeking out the unexpected, keep questioning the systems that power our world, and we will be right here ready to explore the next major breakthrough with you.
Don't forget to like and subscribe for the next episode on While We Were Distracted.